Welcome back to the deep dive. Today, we are taking a look at, well, the rules of the road for the universe itself.
That's a good way to put it.
And we have a pretty specific mission. We're trying to figure out why gravity seems to obey the cosmic speed limit.
It sounds like a simple question, right?
Yeah.
We all know light has a speed limit. We just assume gravity does too.
And for a long time, we assumed they were the same number.
Exactly. We just took it for granted.
But as we're going to find out today, assuming isn't really enough in physics. We've got a stack of research here, but it's all centered around a brand new paper by Qin-Shi Chen. It was published just days ago.
January 2026, yeah.
And it tackles one of the biggest headaches in modern physics.
Yeah.
How to make gravity travel at the speed of light naturally, without, forcing the numbers to fit.
Naturally is the absolute key word there. Because for a few years now, theoretical physics has been in a bit of a, let's say, a crisis mode over this exact topic.
The elephant in the room.
A very, very fast elephant in the room.
So before we get to the solution in Chen's paper, which involves some pretty wild geometry, we need to set the scene. Take us back to 2017. What happened that just broke everyone's theories?
That was the year of GW 117817.
Catchy name. It sounds like my old Wi-Fi password.
It does. It just stands for gravitational wave. August 17, 2017, and it was a massive astronomical event, a binary neutron star merger.
So you've got two super dense stars.
Imagine two stars, each more massive than our sun, but crushed down to the size of a city.
Wow.
And they smashed into each other in a galaxy about 130 million light years away.
And the key here, the really important part, is that we both saw it and we heard it.
Exactly. We detected the gravitational waves, the actual ripples in spacetime, and just 1.7 seconds later, our telescopes detected the gamma rays, the light from the explosion.
Good. Let's just pause on the scale of that for a second. These signals traveled for 130 million years.
A mind-boggling distance.
And after all that time, they crossed the finish line less than 2 seconds apart.
It was basically a photo finish. And mathematically, what it meant was that the difference between the speed of gravity and the speed of light had to be less than 1 part in a quadrillion.
1 part in 10 to the 15.
It's just an unbelievably precise number.
Which is amazing news for Einstein because general relativity predicted they'd be exactly the same. But you mentioned a crisis, so why was this bad news for anyone?
Well, it was a mass extinction event for a whole field called modified gravity.
Right.
See, physicists had developed all these really clever alternative theories. You might have heard of Horndeski theories, for example.
And they were meant to explain things like dark energy.
Exactly. We know the universe's expansion is accelerating, and standard gravity has a hard time explaining why without just, plugging in a fudge factor. So people built these more complex theories.
But they had a side effect.
A huge one. Many of those theories predicted that gravity should travel at a slightly different speed than light. Maybe a little faster, maybe a little slower, but different.
So when the 2017 data dropped,
all those theories just hit a brick wall. To save them, physicists had to start what's called fine-tuning.
Which sounds bad.
It is. It means you have to go into your equations and manually tweak the numbers, just forcing the theory to match that one data point.
It's like buying a suit that clearly doesn't fit and then using 100 safety pins to make it look right.
That's a perfect analogy.
Yeah.
It works, but it's not elegant. It's not natural.
It feels artificial.
And that brings us right to this new paper, Guaranteed Tensor Luminality from Symmetry.
Guaranteed. That's a pretty confident word to put in a physics paper title.
It is, and the whole goal here is to build a theory where the speed of gravity has to be a speed of light. Not because we tweaked a dial, but because the fundamental symmetry of the universe leaves no other option.
We want the suit to fit perfectly right off the rack.
Precisely.
So let's get into the machinery here. Chen isn't using standard Einstein gravity. He's working in a different kind of sandbox, right? Something called Palatini gravity.
That's right. In standard general relativity, we usually focus on just one thing. The metric.
The metric is the ruler. It tells you distances.
Your ruler, yeah. It defines the geometry. If you know the ruler, you can figure out the curvature. Simple.
Okay.
In the Palatini approach, we split that job in two. We keep the metric, the ruler, but we introduce a second independent variable. It's called the connection.
The connection.
Think of it as the guidance system or a map. It tells you how to carry information from one point to another. In standard gravity, the ruler defines the map. In Palatini, they're separate.
Okay, so a ruler and a map, and they aren't necessarily tied together. It sounds like we're just adding complexity. Why do that?
We are adding complexity, but it gives us more freedom. And specifically, it opens the door to something called torsion.
Torsion. That sounds like something you do to a metal bar when you twist it.
That's actually a great way to visualize it. Standard gravity is all about space-time bending. That's curvature. Torsion is about space-time twisting.
A twist in space-time sounds kind of cool.
It does, but traditionally, physicists run screaming from torsion
Why?
because it's messy. It usually creates mathematical instabilities. We call them ghosts, or it adds extra particles, extra degrees of freedom that just shouldn't be there. It's a lot of noise.
So Chen is diving headfirst into this messy, twisting sandbox, but he's bringing a cleanup crew with him.
That's the key. He imposes what he calls a posture, a set of really strict rules to tame the torsion using symmetries.
Let's look at the rule book. Rule number 1 is something about parity and time. A PT projector?
The PT projector, yes. So parity is like looking in a mirror, flipping left and right.
Yeah.
Time is flipping the arrow of time. Chen argues that for a theory to be physically sensible, the observable parts have to live in the PT even sector.
So he's basically applying a filter.
A reality filter, that's a great term for it. It strips away a lot of the complex, imaginary, or handed junk that usually makes torsion theories a complete nightmare.
Okay, so we filter out the junk. Then rule number 2 has this amazing name, the Stuckelberg Spurion.
I know, it sounds like a component from a warp drive, doesn't it?
Totally. Captain, the Stuckelberg Spurion is overheating. What is a spurion?
So a spurion is a tool we use in particle physics, usually to handle symmetry breaking. Think of it as a compensator field.
A compensator for what?
For the torsion. The rule is that the physics shouldn't depend on certain shifts in our guidance system. And to make sure that happens, the theory ties the torsion to this Spurion field. Let's call it epsilon.
So the math doesn't just look at the torsion itself, it looks at the torsion relative to this background field.
Exactly. The only thing that's physically observable is the combination. The torsion trace minus the gradient of the Spurion. Yeah. And the key detail for now is that the Spurion is a fixed background. It's a reference.
Okay, let me see if I'm tracking this. We have Palatini gravity ruler and map are separate. We allow torsion the twist, but we use a PT reality filter, and we anchor it all to the Spurion compensator.
You've got it. And now, this is where the magic starts. Because even with rules, torsion is usually a zoo. You have axial torsion, traceless tensor torsion, all this geometric noise.
But this is where we hit the first big result of the paper, what he calls C1.
C1. The uniqueness of torsion. This is fascinating. When you apply those symmetry rules we just talked about to the equations of motion, the math literally cleans itself up.
It takes out its own trash.
It really does. The equations force the axial and the traceless tensor parts of torsion, the usual troublemakers, to be exactly zero. They just vanish.
So what's left?
Only one piece is left standing, the pure trace torsion. And it's not just floating around randomly. The math forces the torsion vector to align perfectly with the gradient of that Spurion field.
So the twist in spacetime is locked in the exact same direction as this background field.
Exactly. It's a unique alignment that just falls out of the dynamics. It's not an assumption. The system just naturally settles there.
That's incredibly neat. Okay, so we've simplified the geometry. Now we have to actually build the theory itself, the action, as physicists call it.
Right. And here, Chen does something very clever. He explores 3 completely different ways to construct the theory. Think of them as 3 different recipes for the same cake.
Okay, what are our recipes?
Recipe 1 is the ROD method rank 1 determinant. It's very geometric, very structural.
So it's structural cake. Got it.
Recipe 2 is CM closed metric. This one involves deforming or stretching the metric along the direction of that Spurion.
This stretchy cake. Yeah.
And recipe 3 is CS+, which stands for PT even Chern-Simons. This is built from topology from something called the Neon form.
The topological cake. These sound like they're from totally different branches of mathematics.
They are. But this brings us to the second major result, C2, bulk equivalence. Chen proves that when you zoom in to the level where we actually study gravitational waves, these 3 different recipes produce the exact same physics.
So it doesn't matter which path you take up the mountain, you arrive at the same spot.
The exact same spot. They only differ at the very edges of the universe, in what we call boundary terms. But in the bulk, where the waves travel, they are identical.
Which suggests there's something really fundamental and robust going on here. It's not just a fluke of one method.
Correct. And that robustness sets us up for the climax. Pillar C3. This is where we finally answer the big question, does it travel at the speed of light?
Because so far we have a clean theory, we have our recipes, but we don't have the speed limit yet.
Not yet. Now, in many of these modified theories, you have a problem called mixing.
Mixing? That sounds harmless.
Oh, in this context, it's very bad. It means your real gravitational waves, the physical signal, get tangled up with non-physical background stuff. It's like your signal is picking up a ton of static from the wire it's traveling on.
That's unphysical. You want a pure signal.
Of course.
Mhm,
So
yeah.
we enforce a no mixing condition. We take our recipes, a little bit of the determinate cake, a little bit of the stretchy cake, and we ask, is there a specific ratio of these ingredients that makes all that static just cancel out?
And I'm guessing the answer is yes.
There is one unique solution, a locked state. You have to mix them in a very precise way. But here's the magic. When you lock the theory into that no static state, a mathematical identity just pops out.
What's the identity?
The kinetic term, let's call it K, which governs how a wave changes in time, becomes exactly equal to the gradient term, G, which governs how it changes in space.
K equals G.
K equals G.
Okay, now, for anyone listening who might be a bit rusty on their wave physics, why is that one little equation the holy grail here?
Because the speed of any waves is basically the square root of the gradient term divided by the kinetic term. It's the ratio of stiffness to inertia, you could say.
So if G and K are the same number,
Then you're taking the square root of G over G, the square root of 1,
which is 1.
the speed of light.
So gravity must travel at the speed of light.
It has to. Luminality, that's the guaranteed part. We didn't type speed equals c into the theory. We said, we want a symmetric theory with no static. And the math replied, okay, in that case, gravity travels at light speed. No other choice.
It's a structural necessity. It solves the GW170817 problem by design, not by fine-tuning.
The stitching of the fabric, not the safety pin.
That's remarkably elegant, but I have to play skeptic here. It sounds almost too perfect. Is this just general relativity in a fancy hat?
That is the first question anyone would ask. Did you just reinvent the wheel? And at the main level of approximation, what we call leading order, it essentially is general relativity.
So it passes the basic tests.
It does. The paper confirms it propagates exactly 2 degrees of freedom.
Which is what we see, the 2 polarizations of gravitational waves.
Right. No ghosts, no extra weird particles. And it passes the test for matter, too. Because the symmetry's killed off that nasty axial torsion. All our standard particles, like electrons, behave totally normally.
So, if it looks like GR, and it acts like GR, why do we need it? Why go through all this trouble with torsion and spurions?
Because it's only GR at first glance. It matches Einstein's theory at the energies we've tested so far.
Yeah.
But if you look deeper at what we call the next to leading order, or NLO, there's a fingerprint, a unique deviation.
A smoking gun.
A smoking gun, yes. This theory predicts a tiny, tiny deviation from the speed of light, but only at very, very high energies. It's what we call a dispersion relation.
Dispersion. That's like how a prism spits light, right? Different colors or frequencies travel at slightly different speeds through the glass.
Exactly that. In this theory, high-frequency gravity waves would travel at a slightly different speed than low-frequency ones, and the deviation scales precisely with the frequency squared, with k squared.
So if you were to plot this deviation on a graph,
A log plot, yeah.
Yeah.
You would see a straight line with a slope of exactly 2, a slope 2 signature. That's the key. Other theories might predict a flat line, a slope 0, or maybe a slope 4. This one predicts a slope 2.
so it gives us a specific target. It makes the theory falsifiable.
It does. This isn't just a pretty mathematical story. It makes a distinct, testable prediction.
And how would we even test that?
Well, we need a huge range of frequencies. You'd have to combine data from different observatories. You use pulsar timing arrays for the really low frequencies, the future Lysis space antenna for the middle frequencies, and our ground-based detectors like LEGO for the high frequencies.
And if you plot all that data together and see that slope 2 line,
Then this theory is in business. If we see a flat line or a different slope, the theory is dead.
which is what you want in science, a theory you can actually prove wrong.
Precisely.
I also noticed something in the notes about this paper, and I love this detail, is the focus on reproducibility. This isn't just a PDF you have to take on faith.
No, and it's a fantastic trend in physics. Chen provided a full Python repository right alongside the paper.
Audit-ready physics. I love that phrase.
Every figure, every single symbolic derivation, the code to check the uniqueness and the locking, it's all there. You can download it, run it, and prove it to yourself.
That feels incredibly modern. It democratizes the whole process. You don't just have to trust the author, you can run the code.
It sets a very high bar.
So, to recap the whole journey today, we started with a problem. That 2017 neutron-star merger proved gravity moves at light speed, but our theories couldn't explain why naturally.
They were on life support, basically, relying on fine-tuning.
Then Chen comes in, he goes into the Palatini Sandbox, adds the torsion twist, but controls it with this PT reality filter and anchors it with the Spurion.
And those symmetries force the math to self-organize.
The torsion cleaned itself up, the different construction recipes all turned out to be the same, and to get a pure signal, the theory had to lock itself into a state where k equals g.
Which guarantees luminality, the speed of light by design.
It's a really satisfying story. The pieces just snap together.
It is very elegant.
Yeah.
But I want to leave you and the listeners with one last provocative thought.
Go for it.
We talked about this Spurion field, epsilon, and throughout this whole paper we treated it as a fixed background, a rigid scaffolding that defines the rules but doesn't move itself.
Right, the anchor.
But in physics, things rarely stay fixed forever, especially in the early universe or at extreme energies. What if that Spurion does move? What if, at some point, that field acquires its own dynamics?
If the scaffolding itself starts to wiggle.
Exactly. If epsilon becomes a dynamic field, it could open the door to entirely new physics. It might break that slope 2 prediction at even higher energies or introduce completely new interactions. The very mechanism we use to secure the speed of light for our current universe might be the key to unlocking what lies beyond it.
That's a wild thought. The thing that locks down the laws we know might also be the doorway to the laws we don't. It's like finding out the walls of your house are actually made of doors.
That's the fun of theoretical physics. Every answer is just a much better question.
I love it. Well, that brings us to the end of this deep dive. It's a dense topic, but hopefully we've untangled some of that torsion for you.
It was a pleasure.
And if you want to see the math yourself or even run that Python code we talked about, we'll have a link to Chen-Chi Chen's paper in the show notes. It is definitely worth a look.
Absolutely.
Thanks for listening, everyone. Keep looking up and keep asking questions. We'll catch you on the next deep dive.